Thank you for attending my session today. We are going to talk about how to provision Kubernetes clusters on top of bare metal and using open source project called Cluster API and Metal³. So my name is Xavier Avrillier. I work at Giant Swarm as a solutions architect. I focus mostly on our on-premise and hybrid providers environments. And bare metal is kind of becoming the next big thing somehow at the moment. So I just wanted to start with a short statement about the fact that we are in the cloud-native era, not the cloud era, meaning that you can very well be cloud-native and adopt the cloud-native frameworks if you are running bare metal or on-premise environments. This is not like incompatible at all. So I think most of us have seen this thing before. On the left-hand side, we have the traditional virtualization layer with your host OS, the hypervisor, and then for each virtual machine, you have a guest OS. You have your container engines, your binaries, libraries, etc. Whereas when we work with bare metal, we only have our host OS on our physical server, meaning we don't duplicate all these things. We don't have that much overhead. We share the OS, the binaries. So this is kind of one of the reasons why bare metal is starting to make sense at the moment, on top of the fact that there is no, like I'm starting from the last point, but it's mostly one of the most important ones, I would say. There is no virtualization license. Thinking about a specific acquisition that happened lately in the virtualization space. And also we have the case that instead of having resources being scheduled at the hypervisor level, so all your virtual machines need to have their CPU scheduled on the hardware. And then if you run into CPU contention problems, this is kind of going to trickle down in your guest OSs and your Kubernetes nodes. They will think they have all the CPU they need, but in reality, there might be some resource limitations going on. So the obvious one is obviously less overhead. We don't have to have a hypervisor and a bunch of virtual machine guest OSs running. And of course, direct access to hardware. Lately, mostly for GPUs and AI workloads and this kind of stuff, which you can also do with virtual machines, but more efficient with bare metal. However, everything is not pink. Everything is not perfect. Hardware is very slow compared to virtual machine. You can't provision hardware like you provision virtual machine. You can't just pop a new physical metal server in your environment like you would create virtual machines. You have to rack it, configure it, patch it, etc. Hardware breaks, provisioning is very hard usually, so we kind of have to find a way to make it easier and make it more cloud native and more scalable. And this is why we are here today with Metal³, which we are going to talk about in a bit, but first, let's take a quick look at Kubernetes. So what's a Kubernetes cluster? We have first a control plane, which will host our Kubernetes API, etcd, etc., all the core controllers. And then we have our node pool, so a bunch of worker nodes that will run our business logic. So a node pool is a set of Kubernetes nodes that have the same configuration. Usually when you have to run different kinds of workloads on different types of hardware or networking, etc. So provisioning Kubernetes clusters is kind of open to interpretation. There has been lots of ways to provision Kubernetes clusters. Giant Swarm being one of them. We used to have our own operator that would create nodes on AWS, Azure. So we did that before Cluster API came to be. So lots of different solutions in the market, but somehow, at some point, Cluster API from a Kubernetes lifecycle came to be the industry de facto standard for provisioning Kubernetes cluster. So Cluster API is, for those who are not familiar with it, a way to provision Kubernetes clusters and by using Kubernetes patterns. So, reconciliation loops, operators. So we are moving all the provisioning and the logic back into Kubernetes. And if you want to have a look at how we migrated hundreds of clusters from our own home-cooked operator to cluster API, I suggest we can have a quick look at this talk from one of our colleagues who described all the process that we went through. And on screen is a quick depiction, a 10,000-foot view of how CAPI works. So on the left-hand side, we have our management cluster. The management cluster is a simple Kubernetes cluster, a normal, like nothing special, except we run the cluster API controllers. All the logic runs there. And this controller will talk to your AWS, Azure, or whatever infrastructure environment you want to work with. So by creating custom resources in the management cluster, we are going to instruct the creation of our nodes, our Kubernetes clusters, and get all that stuff bootstrapped automatically without having to do it manually. The good thing about that is that you can integrate your GitOps framework practices in your management cluster, so you can describe your Kubernetes clusters as code, have it versioned, code reviews, and all that good stuff that you get from Git. So first, I'm going to have a look at how a traditional CAPI provider works. So we're going to take vSphere as an example because it's a pretty simple one. So called CAPV, Cluster API Provider vSphere, that's what it stands for. So if we create a Kubernetes cluster, we have a bunch of resources to apply to our management cluster. In blue, we have the control plane stuff. So we will describe, in this case, we use kubeadm, but you can use a bunch of different bootstrap providers. So we have a kubeadm control plane where we describe our API server, etcd, how many replicas we want to use, the bootstrap data that we want to use to configure the Kubernetes nodes. And then we have an infra machine template that will describe what the virtual machines should look like in VMware. For the node pools, in yellow, we have pretty much the same logic, except it's kind of split. So we have the machine deployment, which describes number of replicas for like kind of node pool properties of our of this specific node pool. Then we have a kubeadm config template, which is essentially the same as for the control plane, but without any Kubernetes API stuff, of course, and the same infra machine template. Also in CAPI, we have machine deployments, same concept as our pod deployment. So in Kubernetes, you have pod deployment, replica sets, and then the pods. Here, same concept, machine deployments, machine set, and machines. So it really uses the same Kubernetes patterns to manage infrastructure. And then in green, we have the definition of our cluster. So which siders you want to use for your service sider, pod sider, etc. And then the vCenter specific stuff. So what happens when we apply all these CRs, the custom resources? In the case of vSphere, it's just going to check connectivity to vCenter, but with more like other providers like AWS, Azure, you're going to create a resource group, load balancers, all these things. But vSphere is just a simple hypervisor, so we have none of that to deal with. Then, based on the number of replicas in our machine deployment and kubeadm control plane, it is going to create the machine objects, the machine CRs, so there will be one machine per Kubernetes node. These machines will have a bootstrap configuration, so kubeadm config, based on a kubeadm config template that I mentioned. And this information is going to be put in a secret, so that user data is what we are going to use in a bit to configure the nodes. So both the API and the worker nodes that will join the cluster. So after that, how do we provision that stuff? How does CAPV provisions the infrastructure and pass on the user data to the virtual machines? So CAPV is going to use our vSphere machine templates. We give him like a VM template to use to clone the machines from. He's going to clone the virtual machines. Then that user data that is stored in a secret is going to be passed as VM metadata in vSphere. And by using Cloud Init or Ignition, in the case of Flatcar or CoreOS, the initialization provider is going to look in a specific place, which is for the vSphere provider for Cloud Init or Ignition, and use that user data in the metadata to configure the machine. So in AWS, this stuff is stored like in an S3 bucket, I think. here we just pass it as metadata to a virtual machine. And I'm just skipping a whole bunch of steps here, but we do that. We start the virtual machines. The cluster gets bootstrapped with kubeadm init, and then kubeadm join, etc. We have our cluster provisioned on vSphere. We have all our virtual machines. And then going from there, we need to install everything that we need to install in any other Kubernetes provider. So CPI, CSI, CoreDNS, all that good stuff. There are different ways to install that automatically. Like CAPI's own cluster resource sets, Flux Helm releases, but this is kind of up to interpretation on how the organization wants to manage these applications. And this is what it looks like in Kubernetes. So in the management cluster, at the top, you can see the machine CRs represented. So you will have one machine per virtual machine and per Kubernetes node in our workload cluster. And at the bottom, we have an example of cluster CTL, which is a CLI provided by Cluster API, which gives you some interesting tidbits about your cluster, helps with troubleshooting and all these things, initialization of providers, if we do things this way. Again, I'm mentioning, last talk I mentioned, this time I promise. This is a deep dive by a former colleague called Erkan Erol. This talk is just the slides, but it's amazing. It's really good if you want to see a deep dive of Cluster API and really understand how all the components interact with each other. I really recommend it. So, Azure, vSphere, AWS, all that is pretty easy in a way because we have an API to talk to, but what happens with bare metal? We only have a bunch of physical servers in our rack. How do we do that? This is where Metal³ comes into consideration, so pronounced Metal³. And in the next slide, we are going to see how it differs from our other more traditional providers. So here you can see I took AWS as an example. We have our management cluster with Cluster API, CAPI, so for the AWS CAPI provider. And then this CAPI controller talks with AWS, it creates instances, VNets, etc. In the case of Metal³, we are going to talk to the baseboard management controllers, so BMC, Dell iDRAC, HP ILO, all these things which talk Redfish language. And we are going to use Ironic, which is an OpenStack initiated open source project. So Ironic, we'll see in a bit, it's pretty much our backend of Metal³. Ironic is linked to our Kubernetes world via an operator called bare metal operator, we also call BMO to kind of simplify. And bare metal operator watches specific custom resources, definitions in Kubernetes, and then subsequently asks Ironic to issue the API calls to our BMCs. And bare metal operator, of course, is linked to Cluster API via a Cluster API provider called CAPM3. So let's take a look at the components and what Metal³ is made of. First off, just a few core infra things, very basic. We need DHCP for our servers to have an IP, to be able to talk back to Ironic, for instance. We need a web server to serve our OS images, because it's not like AWS where you just choose an instance type. Here we have to build the images, serve them on a web server, and then grab them from there to be able to provision our servers. And of course, compatible servers. You can't really use your laptop to provision bare metal's Kubernetes clusters. So Ironic is API driven. So it is described as, this is from the official websites, API first, and it's a full set of REST API commands. So by just issuing API calls to Ironic, we will be able to talk to any kind of backend hardware. So we don't have to know Redfish by heart or to know any other specific protocols like iDRAC, IPMI, Fujitsu, all these things. So it kind of obfuscate all these for us. And it's made of a bunch of components. So we have the API, which exposes our Ironic API for us. This is what bare metal operator is going to talk to. We have a conductor. This is kind of the runtime that will issue the commands, Redfish commands to our baseboard management controllers. We have a Ironic Python agent, IPA. This is kind of a RAM disk that it's kind of a small image that will run on our physical servers, and it will be our agents. This guy is going to do stuff on our behalf on the physical servers, like writing images to disk, checking configuration, all these things. Then we have an inspector that will collect the hardware configuration of our servers and a database to store all that stuff. And the problem with Ironic, in a way, is that it's not really a cloud-native project. It was started to manage bare metal for OpenStack, but you can run it either as deployment in your Kubernetes cluster or as standalone as in some other way, virtual machines, containers, somewhere else. But yeah, it's kind of put together to kind of be the link between hardware and Kubernetes. Then we have our bare metal operator, BMO. This guy runs in the management cluster because it belongs there. It's going to manage the lifecycle of our servers, not the cluster. But bare metal operator is going to watch bare metal host custom resources. One bare metal host will describe a physical server. So this is kind of how we add a new server to our environment. For instance, if you rack a new rack server, you would create a new bare metal host with specific properties that I will show in a bit. So from the bare metal host CR, we can do a bunch of different things. It's quite powerful in the way that you can do firmware updates. We can stop servers, restart. It's basically a way of issuing commands to our iDRACs, ILOs from Kubernetes, just by changing fields in this custom resource. You can do things like configuring RAID devices, network, etc. And this is the base specs for a bare metal host. So as you can see on screen, we have the IP address of our baseboard management controller, which protocol to use. In this case, we use iDRAC, but it could be just plain Redfish, or PEC-C, sorry. And then we have a set of credentials to issue in a secret, which will be the credentials of our iDRAC. For instance, in this case, it's an iDRAC. Which network card to boot from if we're going with PEC-C, and whether we want to keep the server powered off or on. So this is just the basics. We don't have anything about this server yet, just have the IP and a bunch of credentials. So if I create this, what is going to happen next? Just a quick slide about states. So a bare metal host goes through a whole lot of states in its lifespan. It starts with being creating, then it's being inspecting, provisioning, etc. I'm not going to go through all of this because we don't have time, but the states are the important part of bare metal hosts. And this is a diagram from the official websites, which kind of links all these states together. It kind of looks like a mad scientist's side project, but it kind of starts making sense when you get into it and looking into how these relate to each other. So when I create my bare metal host, at first, very briefly, it will go into creating states in the status field. Then bare metal operator is going to pick it up, and it will put it in the registering state. Sorry. Registering is going to check credentials and validate them against the BMC by issuing API calls to Ironic. From there, when the credentials are validated, we go to the inspection phase. So in our BMC, in our BMH specifications, we only had the bare minimums. We only had like the IP and the credentials. And now we need to find out more about this stuff. So we go to inspecting and asking Ironic to do that for us. And this is where it gets interesting. Ironic is going to instruct the BMC to boot from this IPA RAM disk I mentioned earlier. So Ironic is going to expose this RAM disk on an HTTP server. The BMC is going to pick it up, boot on that image, and then it will start on this. It's a small CentOS image, and just run a bunch of Linux commands to find out information about the hardware, networking, firmwares, all these things. And from there, it's going to populate all that information, send it to inspector, which will expose it back for BMO to consume. And once BMO find out about all this stuff, it will put it in a hardware data custom resource and change the status to available. So available means that we now have a host sitting there doing nothing, ready to be consumed by a Kubernetes node. So it could be either running like powered on and powered off if you want to save some time or not. But we are not running anything, it's just there. It's kind of like having a pre-provisioned virtual machines in your vSphere or AWS environment. And this is what this hardware data looks like. Cut down version, of course, there's a lot more to it, but you can see a whole bunch of hardware things like about CPU, storage devices, etc. And I will bring your attention to the storage device. By default, it will use dev SDA1. So in this case, we wouldn't have to specify which storage device to install on because we have one, but depending on the hardware or sometimes it's kind of random, we might not have dev SDA. So we'll have to find a specific storage device that we want to select and target to install our OS. So in this case, we would use the serial number I picked up with Ironic. So now that server is available, it is not running Kubernetes. So let's do that. So in this case, what does provisioning a server mean? So it is available. We have our bare metal host CR in available state. So the only way the only thing to do to provision a server is to assign an OS image to install. So the one served by the web server called the image server I mentioned earlier. You can build them yourself. You can get images from Exoscale or some other bare metal providers online. There are already some pre-provisioned, pre-created images. We set the image. We set some user data to configure our OS, and which storage device to target. So that user data I mentioned, Ignition or Cloud Init, for instance, looks like this. This is kind of an example. In this case, we are only specifying HTTP proxy variables and adding my SSH key to the server. In a real-world scenario, we would have a lot more to it. But yeah, we just said we create a systemd unit drop-in, and then we restart the service. So this is the secret I mentioned, user data. So the way Ironic is going to put it, or bare metal is going to put it inside our host, not like vSphere where we had to set a metadata field on our virtual machines. Here it's a bit more difficult, it's a bit more tricky. So Ironic is going to create a small partition image called the config drive. We'll serve it for Ironic for the RAM disk to consume. And then once the RAM disk boots, it will create that small partition which will contain all that user data and that ignition configuration. And once it boots, it will pick up that information based on the ignition or cloud init provider that we want to use in this case. So we have this small partition. So this is all obfuscated. It's just like the behind the scene. We don't see any of that happening when we use Metal3, of course. And this is the visual representation of this action. So not necessarily going to go through all of that, but we do the same thing. We have the IP RAM disk that starts. We create this config drive partition with the user data. Then when the host restarts on disk, it will pick up all that data, bootstrap the nodes, create the files, the SSH keys, run kubeadm init, and all these things. So in this case, we only have a few things for the HTTP proxy, but we'll see in a bit how Cluster API changes this and automates it for us. So for Cluster API, we only have the Metal3 provider. And that Metal3 provider is going to do what we just did. So it's going to pick a suitable bare metal host CR. So it's going to look for the available CRs, and we can have specific labels and like filters and targets to target specific physical servers with different properties from each other. And it will populate an image and user data. So that user data is not like a few lines like I did for the proxy and my SSH key. It's going to be populated by our Bootstrap provider. So in this case, kubeadm. And it will be a lot longer. We will have all the kubeadm configuration. We'll have all the files that go into it. So depending on how complex you want your Kubernetes clusters to be, this can be quite extensive. And again, this is what it looks like in a diagram. So once we create our machine deployment, for instance, we're going to have a number of machine CRs based on the replicas, associated Metal³ machine CRs, which will get picked up by our CAPM3 provider, our Metal³ cluster API provider, which will configure our bare metal host with the user data, the OS image, and then we are back to the usual scenario of bare metal operator, ironic, and all that stuff that goes like we described earlier. And if we look at our bare metal host CR after that operation, we'll see that we have an owner reference to our Metal³ machine. So that we know that this bare metal host is currently being consumed by this specific Metal³ machine. And the rest happens pretty much like any other cluster API provider. We are going to first bootstrap our control plane, then our next control planes are going to join, and subsequently we'll have our worker nodes, and at the end of the day, you still need to install your CNI, CPI, etc., to initialize your Kubernetes cluster. A few interesting things. I will say it again, it is pretty slow. Especially when you start adding a new server and going through the inspection phase, it takes a while. Hardware is much slower than virtual machines, of course. But the interesting part is that lies in the cluster upgrade process. So in a in a cloud or virtualization provider, you would easily create new virtual machines when you want to upgrade your cluster. So you go from 130 to 131, you have your cluster running, you create your new control plane node with 131, you delete one in 130, you join it, you delete it, and you kind of do this process of creation, deletion. But with hardware, we might not have the luxury of having spare physical servers running and doing nothing. So what we can do is, instead of doing that, we will scale in instead of scale up. We will first delete a control plane node and a worker node, create a new one. So we deprovision it. We saw earlier the provisioning process. There is the opposite side is kind of the deprovisioning process that works kind of the other way around. So we deprovision it. It goes back from provision to available, and then we reprovisioning with 131, for instance. So this kind of allows us to make use of our hardware in a bit more efficient way. And then we can perform a few operations with annotations on our bare metal host CRs. So, for instance, if we want to change some hardware, add some memory, change CPUs or whatever, storage, we can trigger a new inspection, and that will update all our hardware data. And from there, we kind of related to it, we can assign reboots, reboot methodologies to our bare metal host, or maintenance mode to keep it off. So we can have a set of annotations that will keep our server off, so we can do whatever maintenance we need to do, or reboot it in a different way. So there are a lot more to it, but we don't really have time to get into all these annotations and all the operations that we can do with the bare metal host CRs. But this is pretty much how Metal³ works, by kind of tying the cloud native world with the more traditional infra side of Ironic. And it works pretty well. So thank you for listening, and I hope you enjoy the conference.